Welcome to the Deep Dive. This is where we take a stack of your sources, dig in, and really pull out the key insights. Basically, a shortcut to getting you up to speed. Today, we're diving into, well, the really fascinating world of generative deep learning. The book is Teaching Machines to Paint, Write, Compose, and Play by David Foster. Our mission really is to uncover how machines can actually create new things, not just, sorting stuff or making predictions. You've probably heard about AI doing some incredible things lately, but today we want to really unpack how it moves beyond just analysis to actual creation.
That's absolutely right. Yeah, most machine learning you bump into day to day is discriminative. Think of a model trained simply to tell if a painting is by Van Gogh, for instance, yes or no. But generative modeling, that aims to create new paintings, totally new ones, but in the style of Van Gogh. It's a completely different kind of challenge, and honestly, often much harder to evaluate because, well, how do you judge good art? It's subjective.
Right, subjectivity is a big hurdle. So our goal for you today is to really get the fundamental building blocks, maybe some surprising methods, and these incredible applications. We're talking machines learning to generate completely novel data. It could be art, text, music, or even how to drive a virtual car. Get ready for hopefully some real aha moments. So let's start right at the beginning. What exactly is generative modeling? How is it different from the usual machine learning problems we hear about?
Okay. Well, imagine you have a big pile of paintings. Some are Van Gogh, some aren't. A discriminative model, like you said, it learns to predict if a given painting is Van Gogh. It's a classifier. A generative model, though, its goal is to learn the underlying distribution of Van Gogh's style. It's trying to grasp the patterns, the colors, the brushstrokes deeply enough that it can then produce brand new paintings that look like his. It's really about estimating that true data-generating distribution.
Okay, the distribution of a style. That's interesting. What does that mean from the machine's point of view? Is it like literally learning brushstroke patterns or something more abstract?
It's definitely more abstract. It's not just about classifying things anymore. It's about understanding how something is constructed, down to its core components and how they relate. And this shift, it opens up completely new possibilities for what AI can do. But like I said, challenges too. Evaluating a discriminative model is pretty simple, right? You measure its error rate. How often is it wrong? But how do you objectively measure the goodness or the quality of a brand new generated painting? That subjectivity makes progress kind of harder to track.
Yeah, that makes total sense. So how did the early attempts handle this? When they first tried generative modeling, how did they deal with these challenges?
Well, the book brings up a pretty simple probabilistic model called naive Bayes. It's based on what they call a naive assumption. It basically assumes that every feature in the data, say hair color, is completely independent of every other feature, like wearing glasses.
Independent?
Right. So for a structured data set, the book uses this rodal example with high-level features like accessories type or hair color. And for that kind of data, this naive assumption can actually work surprisingly well. It can generate some reasonable new combinations.
But I'm guessing naive is the key word there. It probably falls apart pretty quickly when things get complex.
Oh, absolutely. You hit the nail on the head. The book gives this great counterexample, Planet Pixel. Here, the data is just raw 32 by 32 pixel images, faces basically. The naive Bayes model, because it treats each pixel independently, it just samples pixels randomly. And the results, they're truly bizarre. Just pixelated noise that looks nothing like a face. It has zero understanding that, pixels next to each other should probably be similar colors, or that pixels near the eyes might form circles for glasses.
Those just random static.
Exactly. And the key insight wasn't just that naive Bayes failed, but why it failed. It showed us really starkly. For machines to create complex things, they need more than just data. They need to understand the relationships, the underlying structure within that data. Much more sophisticated than just assuming everything's independent.
It sounds like something out of like an old video game cutscene, very blocky. So how do we make that leap from those bizarre pixel soups to the kind of sophisticated generation we see now? How do machines learn to understand unstructured data, like images?
Yeah, this is exactly where deep learning comes in. It makes a huge difference. Unlike older machine learning that often needed neat, structured, tabular data, deep learning really excels with unstructured stuff, images, audio, text. And a really critical idea here is representation learning. So instead of us humans having to sit down and define specific features like measure the blondness of the hair, the deep learning model learns which features actually matter. And crucially, it learns how to generate them directly from the raw pixels or raw audio.
Whoa, okay. So it's not just assigning values to features we tell it to look for, it's actually discovering the features itself. That sounds Huge. What does that mean for building these systems?
It is huge. That's where the magic really happens. It finds what's called the nonlinear manifold, where the data actually lies, which basically means it finds the hidden compressed structure within all that messy raw data, the structure that actually makes it meaningful. Think of like a tangled ball of yarn. The manifold is like the single, simpler thread you can follow to understand its shape. The book uses a great analogy, a biscuit tin image. Just looking at the pixels, it's not obvious how you tweak them all to make the tin look taller, but in this learned latent space, this abstract space of features, it might be as simple as just adding one to a dimension the model discovered corresponds to height. This lets you manipulate high-level properties easily instead of getting lost in the weeds with individual pixels.
Okay, that makes sense. So with that foundation, let's get into the big players, the core architectures. Variational autoencoders and generative adversarial networks, VAEs and GANs.
Right. Let's start with VAE's variational autoencoders. Think of an art exhibition, maybe run by two brothers. You've got Mr. Encoder, the encoder. He looks at original paintings and puts little markers on a wall representing them. Then his brother, Mr. Decoder, the decoder, tries to recreate the original paintings just by looking at those markers. They both try to minimize reconstruction loss, make the recreated painting look as close as possible to the original.
Okay, encoding and decoding. Makes sense.
Now, a VAE adds a little twist. Let's call him Epsilon. Instead of Mr. Decoder just using the exact spot where Mr. Encoder put the marker, Epsilon takes that spot as a suggestion, but then samples from a sort of fuzzy area normal distribution around it. This little bit of randomness, this fuzziness, it forces the latent space, that wall with the markers, to be smooth and continuous, structured. And that continuity is key. It means we can generate brand new art, stuff the model's never seen, just by picking a random marker location from that smooth space.
And the book shows some really cool examples of that, right? Like taking a face and just nudging a point in that latent space to make it smile, or add glasses. That, for me, is the real aha moment. It's not just shuffling pixels. The machine has learned to represent and manipulate actual concepts like smiling or wearing glasses in this abstract thought space. That feels like a different level of understanding.
It absolutely is. It's understanding semantics, not just pixels.
Yeah.
Okay, now for Jan's generative adversarial networks, a different beast. Imagine a game. The book uses this fun Ganimals analogy. You've got Gene, the photographer, trying his best to create super realistic but totally fake photos of Ganimals. And then you have Di, the sharp-eyed seller, whose job is to spot Gene's fakes among real Ganimal photos. They basically train each other. Gene gets better at fooling Di, and Di gets better at catching Gene's fakes. It's this constant back and forth.
Huh. So it's like a high-stakes game of cat and mouse between two AIs. What's maybe a surprising challenge or an unexpected finding that came out of Jan research beyond just this game dynamic?
That cat and mouse game, that adversarial process, is precisely what makes them so powerful. The generator network creates the data. The discriminator network tries to tell real from fake. The ultimate goal, for the generator to get so good that the discriminator is basically just guessing, can't tell the difference at all. But while GAMs are incredibly powerful, they are, and the book stresses this, notoriously difficult to train. You run into problems like oscillating loss, where neither network really improves, they just kind of go back and forth. Or worse, mode collapse, where the generator finds one easy trick to fool the discriminator and just keeps producing that one type of output, losing all variety. Like only generating pictures of tabby cats, never Siamese. So lots of research went into fixing this. Things like Wasserstein GANs or WG GANs were developed specifically to make the training more stable and reliable, leading to sharper, more diverse images.
Right, so GANs are super powerful but tricky. But imagine taking that power not just for making realistic fakes, but for actual art. Which brings us to how these deep learning models tackle something as, well, creative as visual art. How do machines paint?
Exactly. The book dives into two really cool techniques for this. Cycle GANs and neural style transfer. Let's take cycle GAN first. Remember our greengrocers, Granny Smith with apples, Florida with oranges. They want to sabotage each other. A cycle GAN learns to translate images from one category, one domain to another, like turning photos of apples into photos that look like oranges. But here's the kicker. Without needing paired examples, you don't need a picture of this exact apple and this exact apple tainted like an orange. You just need a bunch of apple pictures and a bunch of orange pictures.
Wait, no paired images? How does it learn the right translation then?
Through cycle consistency. It uses two generators and two discriminators. One generator turns apples into oranges, the other turns oranges back into apples. The system forces them to work together, so that if you turn an apple into an orange and then turn that orange back into an apple, you should get something really close to your original apple back. That round-trip consistency is the magic trick that lets it learn the mapping without explicit pairs.
Wow. So you don't need to show it a photo of your cat and a Monet painting of that exact cat. It just learns the Monet-ness from a collection of Monet paintings and catness from cat photos. That is incredibly flexible.
That flexibility is massive, yeah. It opens up tons of applications. Now, neural style transfer works differently. It's not about learning a general translation between two whole categories. Instead, you take one specific content image, maybe that photo of your dog, and one specific style image, say Van Gogh's Starry Night, and you merge them. You want the output to look like your dog, but painted in the style of Starry Night. It usually uses a pre-trained network, like VGG19, which already understands a lot about image features. The process then tries to minimize two things simultaneously: content loss, how much the output differs from your dog photo, structure-wise, and style loss, how much the stylistic elements, like textures and color patterns, differ from Starry Night. This style loss is often measured using something called a Graham matrix, which captures correlations between features, like how often do certain brushstroke directions appear near certain colors in the style image. It tries to replicate those statistical patterns.
Okay, fascinating. So moving beyond images, machines can write too, but text feels different. Pixels can blend smoothly, right? But words are distinct units. Change one word and bam, the whole meaning can flip. How do machines handle grammar, coherence, the actual flow of language?
Yeah, text generation is definitely trickier. Partly because its discrete word A is fundamentally different from word B, not like slightly changing a pixel's color. Plus, language is super sensitive to small changes, and it has all these grammatical rules. The classic model for sequential data like text is the recurrent neural network, or RNN, especially a more advanced version called LSTM, long short-term memory network. Anyone who's played with RNNs knows they struggled with remembering things from way back in a sequence. LSTMs were designed to help with that. LSTMs have this internal hidden state, which is basically the network's memory, its understanding of the sequence up to that point, and it updates this memory as each new word comes in.
So it keeps track of the context as it goes along. That seems absolutely crucial for writing something that actually makes sense.
Exactly. Context is king in language. The book explains how you first tokenize the text, break it down into units the machine can handle, like words or even individual characters. Then you embed these units, often words, into vectors' numerical representations. Glove vectors are mentioned as being pretty good because they capture semantic relationships, like the vector difference between man and woman is similar to king and queen. After that, the model generates text one word at a time, often using a temperature parameter to control how random or predictable the next word choice is. Higher temperature means more creative, maybe weirder output. And it also touches on encoder-decoder models for tasks like question answering. An RNN might find potential answers in a text, then another network generates a fitting question for that answer.
Okay, text is complex, but
Yeah.
music, that adds even more layers, right?
Yeah.
You've got pitch, rhythm, multiple instruments playing together, polyphony. It's not just a single stream like text often is. How do generative models handle composing music?
Music is definitely a step up in complexity for exactly those reasons. Polyphony, harmony, change one note, and a beautiful chord can become, well, noise. So the book starts by showing how RNNs, similar to text, can learn to predict the next note in a musical sequence. They even add things like attention mechanisms, which help the model focus on important notes from the past when deciding what comes next, a bit like how a human composer might recall an earlier theme.
Makes sense. But then there's this really interesting pivot mentioned. What if we treat music generation less like text and more like image generation? That sounds like a bit of a leap.
It does sound wild, but it turned out to be a really powerful idea. A breakthrough, really. The core concept is representing the music visually. Imagine a grid, like a piano roll, maybe with time on one axis and pitch on the other. Or you could represent it as a multi-channel image, where maybe different channels correspond to different instruments, or aspects like rhythm and pitch. This visual representation means you can suddenly apply techniques developed for images, like GANs, to music. The book introduces MuseGAN. Think of it like a musical organ powered by AI. MuseGAN is cool because it has separate inputs for different musical aspects: chords, style, melody, groove. By tweaking these independent inputs, you get fine-grained control over the generated music's high-level properties. This approach has led to some amazing stuff, OpenAI actually did a live-streamed concert using MuseNet, where the AI generated music in real time that no human had ever composed or heard before.
Wow, generating music live. Okay, now for something maybe even more mind-bending. How do machines learn to act in the world, like playing a game or even driving a car, especially when there isn't always one single right answer move, just consequences?
All right, this takes us into the realm of reinforcement learning, or RL. In RL, you have an agent, the AI learning optimal strategies, basically learning how to behave through trial and error. Lots of repeated experimentation within an environment. It tries things, gets feedback rewards or penalties, and updates its internal weights or strategy based on that feedback. Learning by doing. The book really highlights a specific paper called World Models and how it was applied to a simulated racing environment. This system is neat because it has three distinct parts working together. First, a VAE, like we talked about, which takes the raw visual input what the car sees and compresses it into a compact latent state, a summary. Second, an MDN RNN. That's a special kind of recurrent network mixed with a mixture density network. It predicts possible future states and rewards, acknowledging that the future isn't always certain. And third, a simple controller network that takes the current state and the predicted future and decides what action to take, steer left, steer right, accelerate.
Okay, wait. I read that the agent can learn to drive inside its own hallucinated version of the environment. Like training in a dream. That sounds absolutely wild. Can you unpack that? What's really revolutionary there? Why does that matter so much?
That in-dream training is exactly what makes world models so revolutionary. It's the core idea. The VAE and the MDN RNN work together to create this internal world model. It's essentially the agent's own internal simulation, its own hallucination or dream of how the environment works. The controller, the part that decides actions, then trains almost entirely within this simulated dream world. It uses an evolutionary algorithm called CMAES to efficiently search for good driving strategies inside its head. And here's the profound part. By building and learning within its own fast internal simulation, the agent can train incredibly quickly and safely. It doesn't need millions of potentially dangerous real-world driving attempts. And amazingly, the driving strategies it learns in the dream actually transfer really well to the real simulated environment. This dramatically cuts down on the need for massive amounts of real-world data, which can be expensive and risky to collect. It points towards AI that can learn more efficiently, more autonomously, perhaps even becoming robust by exploring possibilities internally. It could be huge for robotics, planning, you name it.
Okay, that's pretty mind-blowing. So let's try to wrap this up. What does all this mean? We've seen machines learn to paint like artists, write stories, compose music, even learn to drive by basically dreaming?
Well, what's truly fascinating is just how sophisticated these models are becoming. They're moving way beyond just recognizing patterns to actual, genuine creation. You look at the transformer architecture, the basis for models like BERT and, GPT-3, GPT-4, it's completely changed the game for text generation. And in images, advanced GANs like ProGAN and StyleGAN are creating faces, objects, things that are often completely indistinguishable from real photos. The pace is incredible.
It really makes you think about our own brains, doesn't it? The book hints at this idea that maybe our brains are just incredibly sophisticated generative models themselves, constantly building representations of the world, predicting what's coming next based on all the structure we perceive everywhere. Almost like we're constantly generating our own reality from an internal model.
Exactly. And that leads to a really deep question, doesn't it? If these AI generative models can learn to create art, text, music, and even learn effectively within their own internal dream environments, how does our own brain's ability to pay attention, to form representations, to process sequences, how does that shape our experience of reality? Is the world we perceive the way it is, partly because our brain, our own generative model, has learned to predict and construct it that way? Is it generating our next moment based on its internal models?
Wow. That is a truly provocative thought to leave things on.
Oh.
Is our reality also just generated? Well, we hope this deep dive into generative deep learning has given you a totally new perspective, not just on the creative power of machines, but maybe even on your own mind. Until next time, keep exploring.